We are going to be looking at the next section, which is atomic properties and periodic trends. Actually, I'm sorry, it's electron configurations of ions. So let's take a look at this section. The goals are to write electron configurations for ions of main group and transition metal elements, and to understand the role magnetism plays in revealing electronic structure. So, the electron configurations of ions. There are different ways of doing it for cations versus anions. We'll do the cations first, it's a little harder. But for the cations, the steps are very straightforward. Number one, get the electron configuration of the neutral element. Number two, rewrite in correct SPDF format. Number three, remove the electron from the least stable subshell first until you get the charge that you're looking for. Remember, for a cation, you have to remove electrons. So a cation charge of +1, you remove 1 electron. For a cation charge of +2, you remove 2 electrons. So let's take a look at this iron +2 ion, and let's get its electron configuration. So step one, get the electron configuration of the neutral element. In this case, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. This is reading it off of the periodic table using the SPDF block notation, if you will. And if you count electrons, you can see that the first 3 subshells have 10 electrons. And here, the next 3 subshells have 10 electrons. And the last subshell has 6 electrons for 26 total, which should be right for a neutral iron atom. So number one is the neutral iron atom. Now, the 4s is less stable than the 3d, so we have to rewrite this so that we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Now we remove 2 electrons from the least stable subshell, which is the 4s. So this becomes 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So you can imagine what iron 3+ would look like. Iron 3+ would look like this, only instead of 3d6, it would be 3d5. Anions. The steps are a lot easier. It's the same electron configuration as a noble gas in the same period. Boom. So F- will be the same as neon because neon's in the same period, which is 1s2, 2s2, 2p6. That's how you get the electron configuration of ions. Very, very straightforward. The other concept in this section is magnetism. So we have 3 types of magnetism: paramagnetic, diamagnetic, and ferromagnetic. A paramagnetic element is an element that is attracted to a magnet. And more often than not, it's slightly attracted to the magnet. So you need sensitive equipment to see that the attraction is there. These are elements that have 1 unpaired electron in an orbital. Just at least 1. It can have many, but at least 1. Diamagnetic are elements repelled by a magnet. And again, slightly repelled for most elements, and it's hard to detect. You need sensitive equipment. You can't just hang an element by a string and take it to a magnet and see if it's being repelled or attracted. It's more sensitive than that. These are elements that have only paired electrons, like neon, which has all paired electrons. And when we say paired electrons, we're talking that each orbital has 1 spin up and 1 spin down electron. And then there's ferromagnetic. Ferromagnetic are elements that are paramagnetic. That means they have at least 1 unpaired electron. And when you expose that element to a strong magnetic force, they become magnets themselves. Now, how do you determine if something is ferromagnetic? And the answer is you determine it experimentally. You can't just look at the periodic table and say, oh, that's ferromagnetic, except for one element. One element you know for darn sure is ferromagnetic, and it's the one where the symbol is Fe. So iron is ferromagnetic. Okay, so let's take a look at the configurations of some transition metal ions. So give the electron configuration for copper, copper +1, and copper +2. Are any of these species paramagnetic? And how many unpaired electrons does each have? So these are all cations. So remember the step for cations are 1, get the neutral, 2, rearrange, and 3, take away. Now we're going to do this based on the not knowing that copper's weird. So we're going to look at what copper would be using the periodic table and not knowing that it's weird. So for copper, this is number 1, get the neutral. You have 1s2, 2s2, 2p6, and you should pause here if you haven't done it already. Get the electron configuration for copper yourself and rearrange it and then see what you get compared to me. Okay, great, you're back. So we get 2p6, 3s2, 3p6, 4s2, and then copper would be 3d9. So that's what we expect using the block formation. To rearrange it, we would get 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, and 4s2. So what would copper +1 look like? It would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s1. And what would copper +2 be? It would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. So if we take a look at the real electron configuration of copper, it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. That's the real electron configuration. So what would we get for copper +1 using this? We'd get 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And this goes a far ways to explaining why we have a 3d10 4s1 instead of a 3d9 4s2. Here, if we take away that one electron, the fourth shell is now empty, making this thing far more stable. Okay, and then here, this would be the same as the copper +2 from the other formation. Okay, but this is what I would expect on a test if you did not know that copper was weird. And I'm not asking you to memorize any weird electron configurations. So this is what I would expect on the test. Now, how many unpaired electrons does each have? If we look at this copper here, we've got 1 unpaired. And the reason I know that it's only 1 unpaired is because all of these subshells are full, except for the 3d9, which should have 10 if it were full. And if it has 9, that means there's 1 electron that's not paired. If we look down here at the copper +1, this would have 2 unpaired. Now, how do I know this is 2? Well, the 3d9, I know that if it were 10, everything would be paired because that would be full. So with 9, there's got to be 1 that's by itself, and the 4s is also by itself, 2 unpaired. And here, this would be 1 unpaired also. Now, how about using the real electron configuration? This is 1 unpaired, 0 unpaired, and 1 unpaired. Now, for those of you who are having a little bit of trouble looking at this guy and seeing how that has 1 unpaired, let's look at the noble gas electron configuration, which would be neon, 3s, and I'm going to write out the orbital box notation. So there's your 3p, and then here's your 3d. If I put 9 in here, I'm going to put 1 in each first, and then I'm going to pair them up until I have 9 total. And here you can see we have 1 unpaired. So if you just memorize how many electrons should be in a full orbital, it's easy to predict how many are going to be unpaired. Okay. So electron configurations and oh, did I answer all the questions here? Oh, I forgot to answer. Are any of these species paramagnetic? And the answer is, well, according to this is paramagnetic, this is paramagnetic, and this is paramagnetic. They're all paramagnetic. Now, according to the real electron configuration, copper is paramagnetic, copper plus 2 is paramagnetic, but copper plus 1 is not. Okay, let's look at the next couple of questions here. Electron configuration of atoms and magnetic behavior. Using orbital box diagrams, depict an electron configuration for each of the following ions. So these are cations here. This is weird. Why do they have O -1? That's not a common ion. I don't think germanium plus 2 is common either. Nonetheless, we'll go with this. Okay. For each of the following ions, for the cations, you get the neutral atom first, and then you take away. So for magnesium, we would have 1s2, 2s2, 2p6, 3s2. So for magnesium plus 2, you'll notice I didn't have to rearrange this because they're all in order, 1s, 2s, and 3s. We'd have 1s2, 2s2, 2p6. And this one is everything's paired, so we'd call it diamagnetic. For potassium, we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And potassium plus 1 would be 1s2, 2s2, 2p6, 3s2, 3p6, and this would also be diamagnetic because each subshell is full, meaning all electrons are paired. Germanium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. So I'm going to rearrange this one because we have some things that are out of order. Remember, 3s are more stables than 4. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, p2. So germanium plus 2, we take away these 2 electrons here in the 4p, and we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Now what about O with a -1, which is not usual? Well, here, I told you that the electron configuration of anions is the same as the noble gas in that period. That's if it has the charge that it normally has. So O2 minus would be 1s2, 2s2, 2p6. What about O -1? Well, let's think about this. This is O2 minus. How many electrons should O -1 have compared to O minus 2? And I think the answer is it's got to have one less electron. So that would be 1s2, 2s2, 2p5. And this would definitely be paramagnetic because you have 5 electrons in the 2p subshell, which means it's not full. Now, I'm not going to pull any of this kind of nonsense on you for electron configurations because O -1 really is not a very common ion whatsoever. Okay, let's look at the next question here. Using the orbital box diagrams and noble gas notation, depict the electron configurations of vanadium, vanadium plus 2, and vanadium plus 5. Is the element or any of its ions paramagnetic? So let's take a look at vanadium. So on my periodic table, here's vanadium. So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 1, 2, 3, 3d3. So remember, this first row in the D block is a 3d, not a 4d, even though it's in the 4th period. I'm going to rearrange it, and this is the little thing I do for rearrangement. It's a little pigtail. 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. So why again does the 3d go in front of the 4s? And the answer is it is more stable. Okay, so what would vanadium plus 2 look like? Well, 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, and I'm going to take away those 2, and I'm not going to write 4s0. So this is vanadium plus 2, and vanadium plus 5 would be 1s2, 2s2, 2p6, 3s2, 3p6, and I'm going to take away these 2 and these 3, so I end at 3p6. This guy is diamagnetic because they're all paired. This one is paramagnetic. And this one's paramagnetic because we have 3 that are unpaired. And this guy here is also paramagnetic. Let's see, para, because it has 3 unpaired. And here, to show you the that this has 3 unpaired, this has 3 unpaired, and this has 2 unpaired, I'm going to show you the noble gas orbital box diagram. So these first 3 subshells represent neon, plus these 2, that actually represents argon. So 1, 2, 3, 4, 5, these first subshells I can represent by writing that, argon, because they have the same electron configuration as argon, which has 18 protons, 18 electrons, and these first 1, 2, 3, 4, 5 are those 18 electrons. So for the 3D, I would write 5 boxes. So there's my 5 boxes for the 3D. And remember, Hund's rule says that you put 1 electron in a box before you pair them. So I have 3 unpaired here. And then for the 4s, they are paired. Remember, the 4s subshell only has 1 orbital. So you got to remember that. S subshells, 1 orbital. P subshells, 3. D subshells, 5. F subshells, 7 orbitals. Okay, so this is neutral vanadium. Vanadium plus 2 would be argon. And here we would write 3D3. 1, 2, 3. So there's vanadium plus 2, and then vanadium plus 3. Well, this is not really what you would write. You would write this, neon, and then you'd make a 3s2 and a 3p6. And that would be neon. So here you can see they're all paired. Here you can see that they have 3 unpaired, and here you have 3 unpaired. Looks like my pen might be running out of ink. Yep, I'm getting there. Okay, so that's the answer to that problem. So the next topic we'll be looking at is atomic properties and periodic trends. As you can see here, it's a rather long subject, so the next lecture is going to be a little bit on the lengthy side. But for atomic properties and periodic trends, just kind of as a preview, we're going to be looking at 4 properties. One is the atom size, another is ion size, something called ionization energy, and something called electron attachment enthalpy, which back in the day we just called electron affinity, but now they kind of changed it. And that's all right, we can deal with that. So this one will be a little bit of a longer section, and you want to be prepared for that. Okay, thank you for listening.